Hello and welcome to the show. Today we're going to be talking about power supplies, DC power supplies in particular. Very handy if you don't already have a lab power supply on your bench, and very handy if you actually need to do some work in location. So the first power supply today, using two 9-volt batteries, probably end up looking something like this. Nice and easy to make. You just basically need a screwdriver and a bit of glue. And the second power supply will get a bit more advanced and we'll use an LM317T. Let's get into it. So here's the first project that we've already put together. This one runs two 9-volt batteries wired in series to give 18 volts. The positive comes straight through this inline switch and then through the inline switch to this terminal block. So from 18 volts through the switch, and we've got the positive and the negative on the terminal block. The output comes from this terminal block to the input of the module, and this will take 6 to 28 volts input. The negative or the ground is connected to the ground of the terminal block and the ground of the device, and the positive from the device is connected to the positive over here on the output terminal block. And the negatives are tied together. So what we have, 18 volts through the switch, through the terminal block into the device, and anywhere from 3 to 15 volts out taken from this terminal block here. Turn on the device, get an LED light out to let you know that you've got power going through, and you can power a range of devices from 3 to 15 volts, up to about 2 amps, which is quite a decent amount of output from a module like this. One thing to take note of, there is a voltage drop. So what that means is that you can't get any more power out of the module than you're putting into it, and there is a drop to take into account. We're putting in 18 volts. There's around about a 3 volt drop, meaning that we can only get 15 volts out of this device, and that works out fairly well because it's rated at 15 volts output. If we were putting in the full 28 volts into this device, we could still only get 15 out. But if we put in 12 volts into this device, a 3 volt voltage drop would mean it didn't matter where we dialed this up to, you'd still only ever get about 9 volts out of the device. So 18 volts is a really good measure for this particular module. Okay, so what we have here in front of us are the raw building blocks, the parts that we're actually going to need to make our own version of the portable voltage supply that we talked about. In this variant, we just have a case exactly the same as the other case, about $5. 4 batteries instead of 2. So wire these in series, and we're talking potentially up to about 40 volts. So on a bad day, they'll be 36 volts, 9-volt battery by 4. They're about $10. Each of these little battery holders around about $1 each, and the actual heart of the system will be an LM317T. Just get that close up here. This is in what's called a TO220 package, standard 3-pin. And this is the voltage regulator that we'll actually be using. This gives you anywhere from 1.2 through to about 37 volts output. The downside is there's about a 3 volt voltage drop. So if you're putting in 36 volts, the maximum you'll get out of this package is 33 volts. But that is still more than enough for what we want. Okay, these are between $3 and $4 depending on where you get them from. So all up, we're probably going to be building this package for less than $30, and this includes a $4.95 cheap little multimeter. Now this little multimeter here, it's the cheapest one I could find, but what we're going to use is we're going to use the display here to be able to give us the voltage out after we've dialed in using a potentiometer. Dialed in whatever voltage that we really want out of our device. This will tell us what voltage we've selected, because we don't have anything on this case other than this to tell us what voltage we're selecting before we go and plug something in and power it up. The advantage of doing this, if I wire this in with a momentary switch, and we'll show you how to do this, if I wire this in with a momentary switch, I can press the switch, get a readout on here of what voltage I've selected out of the device, let go of the switch, and I can actually use the multimeter as an emergency portable little multimeter for the project. So forget to carry one, don't have one with you, this might just get you out of trouble. So what we've got now is two basic pieces of wire, and I've already unscrewed the screws on the back holding this together. So we'll pop this open, and we've got a small piece of foam which simply insulates the battery. That just sits in there like that. Just simply insulates the battery and the metal components from touching any of the actual circuit board in the back. And we can just hopefully just pop that out. Okay. Alright, set that aside. Now if we had a look at our multimeter, this is, if we have a look at our multimeter, this is the standard connection that you would apply your red lead to, because we want to measure voltage, resistance and milliamps. So this is the connection, and this is the common ground, always marked as COM. So we want the black lead to be going into this. So these are the two posts, these are the 2 points that we actually want to solder our pieces of wire onto to be able to give us a connection. I'll do that now. Okay, we've reassembled our multimeter almost. Haven't put the screws in because we need to make little slots for the wires there at the moment. But these two wires should actually be able to act as the probes that we were using before. I'll just strip the ends of these. Okay, strip the ends of those. Now again we'll use our 9-volt battery as our test medium. So this white should act as the negative, and the red should act as the positive. Turn the multimeter on, and as we can see it's showing 0 volts. Connect the wires up. Connect the wires up. 0 volts. 9.74 volts. Different battery. It's got a little bit more juice than the old one. So that approach, connecting those two up, will work. So one thing we do need to do is just to make sure that we've got enough room inside our case for our project. This is the interior, so this will be the entire case as it's closed up like that, and inside there will be our circuit once we've made our circuit with the 317T and 4 9-volt batteries. So they're going to take up the most amount of space. So with the 4 9-volt battery holders, each of the pins that are on these battery holders will be bent straight out, so they'll be fairly flush. Just do it now quickly. Okay, so if we bend out just one of these sets of pins, the battery holders will all sit in the case in this orientation. Alright, so I'm pretty much going to have 4 of those, and that is going to take up a fair bit of room inside the case, as you can probably tell. So that gives us a little bit of room down this side of the case for our circuitry, and because the case is fairly deep, this is actually going to go in here like that once I've made a cutout for it, and it takes up roughly that much in the depth, and I've measured it. There's just enough room here for the depth of the 9-volt battery holders and the 9-volt batteries themselves. So what I wouldn't mind doing from this point onwards is getting this mounted in the case now, and it needs to be in there fairly well, so I'm going to probably hit it with a whole heap of hot glue and just set it in the case like that. We'll see how that goes. We'll start making the cutout now. Okay, so there we have it. I've cut out the whole of the plastic case. Very well made plastic case too. This plastic is extremely thick. It's simply hot glued in around these top 2 edges. The wires are still exposed like that, and a little bit too much hot glue around the front here, but I really just wanted to make sure it wasn't going to go anywhere. And as you can see, we still have a functioning multimeter. Okay, on to the next part. Alright, so these are our 4 battery holders, and we'll quickly wire these up in series to be able to give us a 36 volt battery bank. Let's go ahead and do that now. Okay, so there we go. We've put our four 9-volt batteries together and given ourselves a 36-volt battery bank. We'll put the multimeter over it one more time, just to make sure. Okay, there we go. Still getting 38.69 volts. Okay, just before we build our LM317T circuit, I thought I'd lay it out on the whiteboard here. It looks like a little hard to follow, but I'll walk you through it. So this will be our 40-volt battery bank that we've already built. This will provide up to about 40 volts, but generically 36 volts into the circuit. The positive of the battery bank comes directly over to the voltage in pin of the LM317T. This is actually the pin out. This is not the way it's drawn when you look at a circuit diagram. This is how the actual physical pin out of the LM317T works. So the voltage in pin is the far right pin when you're looking at the front of the packet and the front of the actual integrated circuit. The front is where the writing is. So voltage in, voltage out is the middle pin, and the adjustment pin is the pin on the right. Now what happens is you tie the two voltage out and adjustment pins so that on this voltage out mark you have a 200 ohm resistor and your variable resistor, and the variable resistor is the trim pot that we looked at earlier. That gets tied to the negative, and you take the voltage out and the negative common to power your device. So this will be anywhere from 1.2 volts through to about 30, with a 200 ohm resistor, probably about 30 volts output, which is close enough. It's what we would like. So 1.25 to about 30 volts, so maybe 1.275 with a 200 ohm resistor. I won't go any lower than that, to 30 volts output. Let's actually have a look at the physical circuit on a breadboard, and this will make a lot more sense. Okay, so here is our circuit. As you can see on the right hand side here is the 36 volt battery bank, and I've got that coming through to the positive and the negative feeding the power rails on the breadboard. So from this point here, the positive leaves the breadboard, leaves the positive rail and connects to the positive of the LM317T over on this side here. So as you can see, it comes through to the very first pin. See if you can see the pin I'm talking about. There you go. So that connects to the very first pin of the LM317T. The 200 ohm resistor, this one's actually about a 280 ohm resistor. I've got to replace that. So the 200 ohm resistor, this thing just here, connects from the center pin, which is the voltage out pin, to the adjustment pin, which is the very left pin as we look at the front of the LM317T. That is then taken via this orange jumper lead over to the what we'll call the input of this large K trim pot, large 5000 ohm resistance trim pot, and turn the dial, and that's what gives you your variable voltage. So the middle pin of this trim pot is then connected back through to the common ground on the power rail. So voltage out is taken via this red lead here. So this and the common ground voltage rail are where you get your outputs from. And that'll give you, like I said, anywhere from 1.25 to about 30 plus volts. So there's two capacitors that still have to go onto this circuit, but we'll fix that up in a minute. For right now, let's just quickly demonstrate how this circuit might work. I'll hook up the multimeter and we'll go from there. Okay, here's our circuit again. What I've actually done is hooked up the two capacitors that should be in the circuit, and I've got the negative of these little electrolytic capacitors going to ground, and one is connected to the voltage input, and the other one going from ground is connected to the voltage output. These are little 2.2 microfarad capacitors. The important thing about these capacitors is that they are rated at a higher voltage than the output of the total circuit. So if we're putting out a potential of 40 volts, these need to be higher, and these are 60, I think it's 63 volt rated electrolytic capacitors. So that's important. Don't put 16 volt or 24 volt capacitors in there. You can cook them, they can explode, catch fire, and so on. Okay, so I've just hooked up the multimeter to the circuit, powered it on, using the 40 volt power supply or 36 volt power supply that we've made. Now with the capacitors hooked up, and just to show, we still have 33 volt output. That's higher than before. What I've done is this particular resistor here was a 280 ohm resistor before. I've replaced that with a 170 ohm resistor. So we're getting a maximum of 33 volts out, and on the lower end of the scale all the way down to 1.266 volts. Perfect. So what I've done here is finished off the 9 volt battery bank, giving us 36 volts. This is now hot glued in, so it's fairly secure. And I've got 2 leads, one for the positive, one for the negative, and I've got a little auto terminal on the end of that, and I'll show you why in a minute. So that's pretty much finished off. It's ready to put in the case and close up. And this is the actual circuit that I've transported from the breadboard. So what we've got here, this is the LM317T. I've put a heatsink on it. These can get quite hot because they're only a linear voltage regulator, not a switch mode one. So they do get quite hot. So this heatsink is the minimum that I'd probably do. I might need to actually replace this with a larger heatsink, or perhaps even change this to a switch mode voltage regulator in the future if I keep using the module. So I've got the 2 capacitors on there, the little resistor, and the 5K resistor here, the trim pot. So on the back, not the world's greatest soldering job, but not too bad. I've been able to use a lot of these runs on this proto board, which are really handy, especially when you want common ground or a common power rail. And the actual one running up this side here doesn't connect quite to the bottom here, but this one running up the side and across the top is the common ground. So I've got the 2 capacitors touching here, and I've got the output of this trim pot swinging over and also touching the common ground rail here. And this is where the rest of the devices, the rest of the components are soldered through. Soldering job not too bad. I do have to change the soldering iron. I think I'm not getting quite enough heat, and as a result I'm having to hold it on there for quite a bit longer. Some of these solder joints look terrible, but under the microscope they're all pretty clean and not too bad. Anyway, I won't go any further into that. Yes, so this is now mounted on a little circuit board, and I'm ready to put this in the case. Put this in the case, connect a couple of other things up, and we're away. So this is the final project all assembled. So let me just take you through what's finally been done. Multimeter, as you already knew. I've put a terminal block here just to be able to connect something to the external, so that's to the power supply itself. And it's just a bit of hot glue in there holding that in place, but it's also cut in through the case. The 2 probe equivalents coming out of the multimeter are running into the positive and the negative of this terminal block, and the positive and the negative of the terminal block are basically taking their power from our circuit board that we've already made. It's now mounted inside the case here. Still got the heatsink on the LM317T, and I've soldered in and mounted a switch inside the case to be able to turn the device on and off. It never actually had an on and off button before, and that's where I've used those auto terminals coming from the power supply of the battery bank that I showed you before. So if we turn this over, as you can see, wrangle these wires. So the final product will be, once I put the screws in, pretty much this here, and the terminal block is the output down here, and I'll mark that as positive and negative in a minute. So switch, power on, we can test the output voltage by holding in the button. As you can see, the multimeter is currently, or the entire power supply is currently dialed up for 29.3 volts, and let's make sure you can see that, and we just turn our trim pot. That's the maximum that we can get, 33.3 volts, and we can dial all the way down to 1.25 volts. 1.2 doesn't have the resolution. So there we go. Let go of the button. Obviously no power actually going through the multimeter anymore, and we can use these posts to use the multimeter like you normally would. So hold the button in, read your voltage, connect what you want to the output terminal block down here, and away you go. Obviously cancel the power, and there is nothing for the multimeter to read because there's no power going through the device. Well, there you go. Two DC to DC portable power supplies. Very different techniques in making both. One not too hard, $55, about 45 minutes to make. Another one probably the rest of the day, but you can make this for around $30–35. I hope you've enjoyed this video. If you do, subscribe, and if you've got any questions about what's gone on through today's episode, by all means let me know and I'll try and answer them in future shows. Thank you.